see your screen. And so Nicole is going to talk to us a little bit about theoretical nuclear astrophysics and gravitational waves. She's joining us from Triumph today. Nicole, whenever you're ready, take it away.
Okay, thanks so much for the introduction, and thanks so much to the organizers for the opportunity to talk to you today. As was mentioned, I'm at Triumph, but as was not mentioned, I am new to the Canadian community. So I joined Triumph within the last year. So I'm super excited to be able to talk to you all today and sort of introduce myself to the community. And just a quick note right here at the beginning, since I'm new, I am looking for graduate students. So if you are a graduate student, or if you have somebody in mind after you see my science, please reach out to me. Okay, so I'm going to take a little bit of a different approach from the other talks that we've seen, and I'm going to take a bit of a zoomed out view and look at nuclear astrophysics and gravitational waves rather than focusing on LISA right away. So let's get started. So it's been 65 years of nuclear astrophysics this year, actually, very exciting birthday for nuclear astrophysics. So what we've known for some time from this seminal work, B squared FH, we lovingly call it, from 1957, was that multiple nucleosynthesis sites have enriched the solar system. These are the solar abundances as a function of what we call mass number in nuclear physics. And you can see that they've already labeled in here several different groups. So you have different elements being formed dominantly in different processes, things like the Big Bang, things like stellar processes. And then when you get to heavy nuclei, you have to have neutron capture processes. So things like the R process, rapid neutron capture, and the S process, slow neutron capture, were already identified 65 years ago. And here you can see in the periodic table where we think most of these processes are occurring. I have boxed this R process. This is my particular area of expertise. And if you look this up online, this will say neutron star mergers. So I have made it more general because hopefully at the end of this talk, I will have convinced you that that is still an open question, okay? So like I said, 65 years, we've known that there's been multiple nucleosynthesis sites that have enriched the solar system. However, things have evolved in the last 65 years. Previously, only a couple of processes were identified originally, but now there are more and more processes that you can find in the literature. So here on the right I'm converting to what we look at in nuclear physics, the ZN plane, number of protons, number of neutrons. These black boxes are stable nuclei. The light gray is where we have information about these nuclei, and the dark gray is where we do not. So you can see where a lot of these processes operate, different sides of stability, as we call it, and also different reaches from stability into these very neutron-rich regions for the R process, into this unexplored territory. So we have all of these processes now, and the ultimate question is the origin of the elements. How are these processes contributing to the inventory of the elements that we actually see? So as I mentioned here, you have this nuclear physics dependence. You can, particularly for heavy elements in the R process, you're moving into regions where we don't have information on these nuclei. So we are reliant on theoretical models, nuclear theoretical models, et cetera. And therefore, we're reliant on nuclear physics that we have to input in our calculations. However, the big point here is just that observables in general are going to depend on the properties of exotic nuclei, some of which we have the information for, some of which we don't. So this is the example with heavy elements. You're going to see lots of examples with heavy elements and binary neutron star mergers because that's my particular area of expertise. But nevertheless, so you have neutron capture, photodissociation, beta decay. These types of processes are essentially determining how you produce heavier and heavier species when you stop producing heavier and heavier species. For example, the R process can get up to things and be terminated by fission. So I have just claimed observables depend on the properties of exotic nuclei, but if this is something that's new to you, if you're a student or something, I can prove this to you very quickly. So as you can see from this picture, the R process is reaching very far out from these stable nuclei. Very, very neutron-rich nuclei are being populated. And when they encounter these areas right here, called the closed neutron shells or magic neutron numbers, this is a region of especially stable species. So you want to kind of hang out there. They don't want to capture away, and they're hesitant to beta decay a bit more than local species as well. And you can see that that leads directly to these peaks right here. So since the R process is very far from stability, once it starts to decay, its peak is going to be shifted to the left relative to the S process. So this is just a quick proof that the observables that we see, it's very obvious, right, even in the abundances, depend on the properties of exotic nuclei. Okay, so not only do we want to know where things were formed, we want to know when things were formed. We have this new zoo of nucleosynthesis processes these days, but how much matters for which element? And this is something that you have to use something called galactic chemical evolution to start to get at. So this is the general picture of galactic chemical evolution. You have different stellar processes occurring. You have things like supernova happening. You have more exotic processes like collapsars and magnetorotationally driven supernovae happening. These are some R process candidates, for example. And then they can create remnants, and then the remnants can do interesting things and have interesting nucleosynthesis processes occur. When these things occur, they can eject material into the interstellar medium, new stars form, and the process continues. So how do gravitational wave detections inform this picture? Well, I'm going to use binary neutron stars as an example. And there's three ways in which they are going to inform this picture. One, event identification and electromagnetic follow-up. Of course, we're going to have a very famous example in a minute. Information about the neutron star equation of state and the neutron star merger rate in the local universe. So let's get started by seeing how event identification and EM follow-up has informed what we now know about heavy element nucleosynthesis. So yeah, this may be very well known to this group, to most people in this group, but I still want to go through it just because there may be some misconceptions lingering within the community that I would like to pull out of the woodwork here. So here are the R process abundances. Once you take that solar abundance that I've shown and you take out what you expect for the S process, these are called your R process residuals. For a visual reference, this is where the lanthanides live. That's a particular type of element. This is where silver lives, and this is where gold lives. So if you heard a bunch of things in the media about gold and GW 170817, this was an assumption, essentially. This went a bit too far, as we'll see. So what was seen was the light curve, of course, and the argument is that if you have lanthanides or actinides present, you have an opacity that increases, so you have a longer duration light curve shifted towards the infrared. You can see this explicitly in this model here by Dan Kaysen, where as he increases the number of lanthanides here, the light curve shifts and it moves towards the infrared. So let's compare to what was seen in observation for GW 170817, and you can see this explicitly. We have an early blue dominated blue kilonovae, and then followed by this later dominance of IR right around these later timescales of days. So here you can explicitly see that at least lanthanides were present in this material. But this isn't a closed case because lanthanides are not gold. So you can say that you made lanthanides, maybe you made some gold, but did you make a solar amount of gold such that you are now can be the dominant contributor of gold to the solar system, for example? That's a hugely open question still. Additionally, we don't know if actinides are all the way up here. So evidence for lanthanides is not evidence for actinides, and you can't really decouple these things by just looking at it in this way. So let's talk a little bit about actinides and mergers. So once you have mergers and you have this very neutron-rich ejecta that can get out, how you're treating fission within your theoretical calculations to predict the abundances really adjusts your lanthanides. Here, if you remember, is where your lanthanide abundances were. So our predictions for our lanthanide abundances depend on how we treat the split of these nuclei. And this is not known in the nuclear physics community. How the nucleus neutron-rich nuclei split, the rate at which they fission, etc. These are unknown things. Okay. Additionally, the energy that fission releases during a process is just huge. You have something like a 200 MeV Q value. So if you have that kind of energy on timescales on the order of your expansion timescale, you can have some significant effects on your light curve. So for example, californium-254 is something that's known to have a spontaneous fission half-life on the order of 60 days. And we found in a calculation that we were producing this species with a given nuclear set of inputs. It's produced to varying degrees with different inputs, but it's produced to some degree with all of these. You can also see that it's right on the edge of what we know for nuclear data. This black line is the limit of our knowledge of nuclear data. So there's a lot of interesting things that could be happening in this region. Are there more things like californium? Is californium even populated? Maybe there's some fission down here that could prevent it. But nevertheless, when we apply our theoretical rates, what we found was that if you populate this species, you get a significantly higher prediction for your absolute magnitude of your light curve with the species populated as compared to without. So this could be something that you could look for at late times to look and actually answer the question of whether or not actinides were produced. Another thing that I wanted to bring up was MEV gamma rays. So this is something, of course, we would need a galactic merger, but nevertheless, I would like the community to be aware of. We found that anything that's a gamma ray above 3.5 MeV from a neutron star merger is likely coming from a fission product, okay? So usually at these later times, you are more near those stable species, so you're getting gammas from beta decay and they are falling in this lower energy range. However, if you have fission, you have a more continuous spectrum here, so you're getting these higher energy gamma rays from fission. So this is another potential signature that actually we've reached actinides in a future neutron star merger observation. Okay, so that's how we were able to learn about nucleosynthesis from EM follow-up, which was only possible because the gravitational waves pointed us in that direction and told us what that event was. Next, I'll talk a little bit about the neutron star EOS. So you may be familiar with the fact that you can use information from the waveform and tidal deformation, et cetera, from the actual gravitational wave in order to learn about the neutron star EOS. That's not the piece I will talk about. I just wanted to highlight that that information about the neutron star EOS does feed into the nucleosynthesis, because what you expect for mass ejection in general depends on the EOS. You can see this if you look at hydro simulations, some of the latest hydro simulations, for example, from David Radice and his group. They found that softer equations of state are just ejecting more mass overall, and how much of each type of ejecta you get from an event is also dependent on the EOS.
Nicole, I'm just jumping in with a 2-minute warning.
Sure. Neutron star merger rate in the local universe. So what we did as well after GW 170817 and the first wave of papers was to take a look at, okay, so we now have a merger rate that we have from GW 170817, but is this enough to make the heaviest of elements? So we took light curve, we took light curves to give the mass ejection range from the literature of GW 170817, along with nucleosynthesis predictions. You can see this is using 10 different theoretical nuclear models. We have to take into account that we don't know the abundance pattern that neutron star mergers produce. So we put in that uncertainty, and this is what we get. So you can see the light purple is when you consider those nuclear physics uncertainties, and the dark purple is when you do not. So clearly we have to pin down some of this information to actually be able to answer the question, because there are regions here where neutron stars just aren't going to make enough relative to what's reported. And as LIGO keeps going and updating these things, you can see this is the updated rate. We're going to be able to get more and more refined, and we're starting to look at more and more elements. This is a preliminary plot that we've put together where the idea is now, okay, before we had this band of nuclear models, let's start taking that apart and looking at all of these individual nuclear models. What are these LIGO rates telling us? Is it possible, given different nuclear models, that this is our source? So for example, if you have a model down here, this can be ruled out because you are already saying that LIGO has more mergers than you need to make the solar system abundances, so it doesn't work. Okay, so I just wanted to quickly note that this is a huge region of study within the nuclear physics community. Experimentalists and theorists are both approaching these very neutron-rich species to try to inform these calculations more. So now that I've used this as an example of how gravitational waves can inform the picture of nuclear astrophysics and where and when the elements are forming, I'm just going to have some thoughts here on what future detections might be able to do with other things like LISA and the Cosmic Explorer. So if we are able to see neutron star merger rates as a function of cosmic time in the future with more advanced ground-based detectors like the Cosmic Explorer, that would help tremendously to understand the evolution of those systems and therefore how much they can contribute to the inventory of the elements as a function of time. Supermassive black hole merger rates are going to inform galaxy evolution simulations, so they provide insights on star formation for GCE models. Insights on white dwarf merger rates. Are these the supernova type 1 progenitors? Iron is something that is followed in GCE simulations, but nevertheless, how much iron is coming from where? From white dwarf, from core collapse supernova, etc. This is something that could be better constrained if we knew more about white dwarf mergers. And with that, I will stop there and thank you for your time.
Fantastic. Thank you for the great talk, Nicole, and welcome to Canada. Sorry, I didn't say that right at the start. I know myself, my research group, John Runn, his research group, we're all really excited that you're here and to talk more science with you. We have time for a quick question if we have any from the audience. Okay, there's one in the chat here from Nick Vieira. So not super LISA connected, but we'll throw it out there. You hinted at the fact that it might be tough to distinguish lanthanides and actinides. What would be the smoking gun evidence for actinide production and neutron star merger? Do we really need some sort of CF 254 bump in the light curve at late times, or could spectra provide some insights?
Yeah, spectra, goodness. I mean, my understanding is that that's going to just be so difficult to actually see any kinds of lines for that. But yeah, this is why I brought up MEV gammas, because it's another bulk property. These are just sort of bulk properties that fission. If you have some very high heating at later times, it doesn't even have to be CF254. In fact, in some of our models, we see some Rutherfordium isotopes pop up and provide quite a lot of heating. So it's just, if you have fission at late times, you have a lot of heating and it affects your bolometric light curve. So not just CF. But also these MEV gammas are something that we're pretty excited about. That's something we identified as a smoking gun.
Awesome. Thank you very much, Nicole. There's more questions popping up in the chat, but I think we have to move on. So please, Nicole, if you've got time, it'd be great if you could follow up with folks in the chat and keep that conversation going.
Sure.
Up next,